Okay, good day. This is dual enrollment pre-calculus. I am Mr. McCully, and this is lesson number 16, radians and degrees. Let's get right to it. Okay, so, wrong one. Uh, the learning goals for today, we're going to use radian measure. We're going to also talk about that in conjunction with degree measure, and we are going to find and calculate linear and angular velocity. None of these things are extremely difficult, but there are a number of different things that we have to go through as we start a new unit. So first, let's start with the definition. A radian is a method of measuring angles based on the circumference of a circle. Remember, circumference of a circle was 2 pi r, and so you'll see that relationship here. But essentially, most of you have been measuring angles with degrees, and that's all fine and well, but calculus doesn't work with degrees. So if as far as angles go, so we needed another way to measure angles, and so radians is it. And so think of it this way. We've got a couple of topics that I want to talk about. And so if I have a red angle here that is in the standard position, that means that its initial ray is going to be along the positive x-axis. And then if it opens positively, it's going to be going clockwise. If it opens if it opens counterclockwise, it'll be counted as a positive value, and if it opens regular clockwise, the way we would normally see it, it's going to be a negative value. Now, in a in degrees, all the way around a circle is 360 degrees. In radians, it's 2 pi radians. And so if I open an angle up to here, this ray is called the terminal ray, and we could have multiple terminal rays, and those multiple terminal rays are called coterminal rays, meaning that we have this terminal ray that opens up and goes all the way around and then further to be in the same position that this one is. That would be a coterminal ray, and we're going to talk about positive and negative ones later. Now, I know so far you're probably real confused because we've got these curves. Let's talk about it in terms of lines, just kind of like a line segment, like a number line. You are used to, up until this point, having 0 degrees being the smallest angle, and then all the way around the circle being 360 degrees. Now, radians match up 1-to-1 with that, except we have a different top number. Instead of 360, it's 2 pi. And we're going to leave things in terms of pi. All right. And so if you want to equate these values, 360 degrees is equal to 2 pi radians. If I cut this line segment in half, halfway between 0 and 360 would be 180 degrees. Halfway between 0 and 2 pi would just be pi radians. So 180 degrees and pi radians match up. If I cut it in half again, let's say I cut this one in half, halfway between 0 and 180 is 90 degrees. And so halfway between 0 and pi would be pi over 2 radians. So if I go back here, a 90-degree angle is a right angle. And so in radians, pi over 2 would be that right angle. All right. So I'm not going to do all of them here, just enough to get us started, but halfway between 180 and 360 is 270. And so halfway between pi and pi and 2 pi is 3 pi over 2. And we're going to talk about counting in terms of pi just here in a little bit. Um, but clearly 270 degrees and 3 pi over 2 radians is also equal. And just as one more little instance, go back to that original graph that I had here. A semicircle is 180 degrees, and in terms of radians, it would be pi radians. if I match all of these up, there is a linear relationship between degrees and radians. All right, it's just a scalar multiple. And so we have that. If we want to convert from radians to degrees, then all we have to do is multiply by this conversion factor, and that's that 1-to-1 linear relationship. So if I had pi over 2 radians, um, and I multiply it, I think I have an example of converting, maybe. I don't I have an example of that? Yeah, I do. Okay, we're good. We'll come back to it. All right, so here we go. And then if you're converting from degrees to radians, you multiply by pi over 100, 180, and just reduce the fraction. And I got an example of that. We'll do it here in a little bit. Okay. Another example of coterminal angles. We want to talk about this. So given pi over 2, so this angle right here is pi over 2 radians. Find two coterminal angles, one positive and one negative. Okay, so let's talk about the positive value first. So my positive value, we'll go like this, Positive. All right, it's going to start in the standard position that we started for the first one. It's going to go up to that one and then go all the way back around until we get to here. So it's the pi over 2 plus a circle. So it's pi over 2 plus a circle. Well, a circle we already know from a previous slide is 2 pi radians. So here's what we're going to do. We're going to take this uh, pi over 2 and then we're just going to add 2 pi. Now we can't do that. We can't add that because we got a fraction and a whole number here. So I need to convert this into terms, and what I want to do, I want to change my thickness here so that we can see it. All right, so I need to find common denominators. And so how many halves are in 2? Well, there are 4 halves in 2. 4 divided by 2 is 2, and I keep my pi. And so I've got 1 pi over 2 plus 4 pi over 2. That's equal to 5 pi over 2. So this is my positive coterminal angle. All right, let's pick a different color. And let's have a smaller. All right, so if I want to move negatively, I'm going to start in the standard position and I'm going to go clockwise until I get there. All right, well, I don't have to go all the way around, so it's not going to be exactly pi over 2. It's not going to be exactly 2 pi radians. It's going to be something smaller than that. And I could do it by counting. I could count it this way. In fact, let's count to start. But I do want to get something like this so you have an idea of how to make a calculation without having to draw a picture every time. Every quarter turn is 2 pi, or pi over 2, excuse me. So I go negative pi over 2, negative 2 pi over 2, negative 3 pi over 2. So this right here is negative 3 pi over 2. So negative 3 pi over 2 is my negative coterminal angle. All right, so how do I do this with a calculation? Well, it's not all the way around. It's pi over 2 away from being a full 2 pi radians. So here's how we're going to do it. We're going to start with that original value, the pi over 2, and this time though we are going to subtract 2 pi. And just like in the last one, for us to do that, we have to have a common denominator. So we'll just convert it into the same values that we had before. So negative 4 pi over 2. And so 1 pi over 2 minus 4 pi over 2 gives me negative 3 pi over 2, which is what we had. And so we're good. Next one, converting minutes and seconds to a decimal. I think that you're going to want to do this every time. So in a couple places, you're going to see this kind of notation. So 32 degrees 15 minutes, 20 seconds. That's what that says. So 32 degrees, 15 minutes, and 20 seconds. All right, so we want to convert this into a decimal. And you're not going to see it a lot, but you'll see it every once in a while. And so we're just going to do this every time just to be consistent. All right, so remember here you want to kind of consider degrees to be our hours. There are 60 minutes equals 1 hour, and 60 seconds equals 1 minute. All right, so if that's true, then 60 times 60 seconds would be 1 hour. So 3,600 seconds is 1 hour. All right, and what we can do is we can use these conversion factors, and that's what they are. We can use these conversion factors to change this 15 minutes into a decimal value. So essentially what we're going to do is we're just going to leave that 32 there, and what we're going to do is we're going to add. Well, if I have 15 minutes would be 15 over 60 hours, all right, or degrees in this particular instance. And again, since we're thinking of degrees as the hours, all right, we want to change seconds into hours. Well, we use this conversion factor. So it'll be 20 over 3,600. So this is a real quick and easy way to change this to a decimal value of degrees. So if I grab my graphing calculator, I go back to the standard value mode, and I go clear everything out. I go 32, and then I delete that decimal place. And I go plus 15 divided by 60 plus 20 divided by 3,600, and I hit enter, and now I've changed my minutes and seconds into a decimal value, and so I get 32.256 degrees as my final answer. So 32.256 degrees, that is these minutes and seconds changed to a decimal. All right, arc length. A portion of a circle is its arc. And so we have, when theta is a radian, our arc length S is determined upon the central angle, theta, and our radius. So we just multiply those two together and get that. Now, here's where the relationship between radians and circumference comes in. All right, the circumference is all the way around, right? So if I were trying to find C, I still have my R there, but my theta all the way around is 2 pi. Hence, circumference is 2 pi R. You always put your constants in front. Now, if theta is in degrees, you start with your 2 pi R, and then you do a conversion factor, theta over 360. And that's how you move on from that. All right, so let's move on to linear speed. Linear speed for circular movement. So you think of a point on a circle moving around and around. A point moving along an arc S at a constant speed is the distance traveled by the time t. So you find out how far that arc length is, and in most cases, the arc length is multiple circles. Excuse me, and so you just find the distance that point has traveled and you divide by the time it takes to travel, just like regular speed, and you're done. Angular speed, though, measures how many degrees or radians the point on the end of the circle has traveled. So if theta is an angle in radian measure, the corresponding to an arc length S, then the angular speed is the number of radians divided by the time. So you calculate the central angle, and that central angle could be multiple revolutions divided by the time. And so I kind of think, and this is a real loose analogy, the difference between linear speed and angular speed is this difference between miles per hour and RPMs. The only difference with RPMs, it's revolutions, and so you'd have to change your revolutions to degrees. So miles per hour calculates the speed that your car is traveling as the wheels turn. Um, Angular speed calculates how many degrees each of those tires has traveled over that same time. Now, another way for you to think of that, and this one I think is a little bit easier to digest. Picture a Ferris wheel, okay? And so most Ferris wheels have the little carriages that the people sit in on an outer wheel, and then they have another inner wheel of lights, okay? So think of an inner wheel of red lights and an inner wheel of blue lights, okay? And so as that red and that blue light travel around the circle, all right, they will have a similar either linear or angular speed, but they will have a different, or they'll have one that's the same and one that's different. And so think about it this way. Which one will it have? So you might pause and just think about it for a second. Will they have the same angular speed or will they have the same linear speed? All right, or will they have different angular speed and a different linear speed? Thought about it? Took a pause? All right, well, here's the answer. They will both have the same angular speed. All right, because if we draw the dotted line through the middle and we calculate how many degrees that they will travel, they will both travel the same number of degrees in the time frame that we've talked about. But clearly, as they go around, the B travels a much shorter distance than the R travels. So in the same time, because they don't travel independently of each other, because R travels further in the same amount of time as B travels the smaller circle, clearly they have different linear speeds. And R has a faster linear speed. Okay, it's good. Let's talk about some examples here. Convert 315 to a multiple of pi without using a calculator. We can do that. If you go back to this slide right here, we have our conversion factors, so you can look those up. And so if I have 315, the conversion factor, what we're going to do is we're just going to multiply that by pi over 180. And we're not supposed to use a calculator. So what we're going to do is we're going to do some reducing. Let's see here. I can reduce a 5 out of each of those. So 35 divided by, start over, 31 divided by 5 will give me a 6 plus 1 left over. And so I've got 15 divided by 5 would be a 3. 18 divided by 5 again would give me a 18 divided by 5 will give me a 3. And let's see here. Yeah, with 3 left over, and then 30 divided by 5 will give me a 5. So, and then 63 is a prime number. No, it's not. It's not prime, but it's only divisible by 3 and 21. And oh, maybe we can divide 7 out of that. So let's see here. 7 goes into 63 9 times. And then 7 goes into 35 5 times. So I'm going to have a final answer. I've got all that's left is 9 and 5. 9's on top, so 9 pi over 5. And we are good to go there. Convert 5 pi over 6 to degrees without using a calculator. So we'll again start with a 5 pi over 6. This time, since we're changing from radians to degrees, all we need to do is flip our conversion factor. We'll put the 180 over pi here. And you'll notice that the pi's cancel out because I got pi on the top, pi on the bottom. 6 and it is both a factor of 6 and 180. So if I divide a 6 by 6, I get 1, and then 6 goes into 80, or it goes into 18 three times, and I've used all of the values, so I just have my 0 times, or 30 times 5 is going to be 150 degrees, and that's the correct answer for that one. All right. Find the complement and supplement, if possible, of the following angles. So complements is two angles that are 90 degrees or pi over 2. And then supplements, that's going to be 180 degrees or just pi. Okay, so in this case, if I have 65, then I have a complement of 25 degrees because 25 and 65 is 90, and I can have a supplement of this one if I subtract 65 from 180, I'll get 115 degrees. Yeah, that's right. All right, so find the complement and supplement of possible of 2 pi over 3. Well, if I just real quickly draw in the standard position an angle and it goes open to here, this value right there, that is going to be bigger. This is 2 pi over 3. That's actually bigger than pi over 2. So since it's already bigger than 90 degrees, there is no complement. All right, because it's too big, so none. N-O-N-E. All right, and if we talk about the supplement, all right, if we talk about the supplement goes to 180 or pi. And so if I want to figure out what the supplement is, all I'm going to do is I'm going to take that pi and I'm going to subtract away because I just need this portion right there. I'm going to take that pi, which would be right here, and I'm going to subtract 2 pi over 3. Well, I don't have a common denominator, so how many thirds are in 1? There are 3 thirds in 1. So 3 pi over 3 minus 2 pi over 3 is just pi over 3, and that is my supplement. This, and we don't care about that. All right, next one. It says, a circular blade on a saw has a diameter of 7.25 inches and rotates at 44,800 revolutions per minute. Find the angular speed in radians per minute. Okay, so we have this, so this is what we're going to solve using unit analysis. Now, some of you, if you've had chemistry, you've probably done a little bit of unit analysis, and in physics, it also does it. And what you can do is if you manipulate the units, you can possibly get away without having to memorize an equation. So I'm starting with 48,000 revolutions per minute, and I want to get to radians per minute. All right, well, I've already got minutes on the bottom, and so that's good. I don't have to do a whole lot of work there. But I need to change my revolutions to radians. All right, so here's what I want to do. I'm going to multiply by a conversion factor. And I need to get that conversion factor to have a revolutions on the bottom and radians on top, or at least get something that gets me closer to that. But every time you go around one time, we already know that you have 2 pi radians. So my revolutions cancel, and if I multiply 4,800 by 2 pi radians, and I'm just going to leave it in terms of pi. If you want a decimal, you can. But 48 twice would be 96, and so this is going to be 9,600. Copy your zeros. 9,600. Keep your pi on there, so 9,600 pi radians per minute. Okay, Find the linear speed in inches per minute of a point on the tip of the saw. So you've got this saw with teeth on it. I'm not going to draw it on. And we have this. And this radius here is 7.5. And they want us to figure out what the linear speed in inches per minute are. Okay, so we start once again with 4,800 revolutions per minute. And we want to get to inches per minute. Now again, the good news is minutes on the bottom, minutes on the bottom. All we have to do is convert revolutions into inches. Okay, so for every one revolution, all right, for every one revolution, okay, it's going to go one circumference. So one revolution equals a circumference. All right, so what we're going to do is we're going to multiply by our circumference, and we can calculate that. The circumference is 2 pi r in this case, so 2 pi times 7.5 inches, which will give me 15 pi inches. So 15 pi inches. And again, revolutions cancel. We have inches on the top. That's where we want them. We've got minutes on the bottom. That's also where we want it. So we're good there. And just because inches per minute, we usually don't measure inches in terms of pi, I am going to use a calculator on this one. And it's just going to be 4,800 times 2 times, oops, let's go back here. 15 is what I really want. So let's go back here. 15 times second, and there's a little pi button right there. Hit enter. So 22, well, 226,194.671. So 226,194. 226,194. Let's go back. 671.671 inches per minute. That's quite a bit, quite a few. And just so we have an idea, if we know that this is inches, so if I divide that by 12, that'll be feet per minute, right? If I divide that by 5,280, oops, I need to divide by 5,280. Oops, what did I do? Go to, let's clear this go. Second answer divided by 5,280. There we go. So that's 3 miles every minute. That's pretty fast. Those saw blades, they cook. Okay, well, that's all I got for today there, folks. So it's the Super Star Wars fun fact of the day. It's a trap is a line we all know from internet memes, and it does come from Episode 6, Return of the Jedi. But in the original script, it was written as it's a trick, but it was changed after a test screening to It's a Trap because It's a Trick didn't play well. That's all I got. You guys have a good day. Goodbye.